Can you believe it? We might actually be living inside a black hole that exists within a much larger universe. Our entire universe could be nothing more than a projection from within a black hole embedded in a higher dimensional space. Back in the 1970s, Stephen Hawking and Roger Penrose discovered something remarkable while studying gravitational singularities. At the center of a black hole lies a point of infinite density, a singularity that causes the collapse of both space and time. Then in 1974, Hawking went even further. He found that black holes aren't completely dark after all. They actually emit particles in a specific way, a phenomenon now known as Hawking radiation. This discovery not only overturned our understanding of black holes, but also opened up a whole new kind of thought experiment. If information can escape from a black hole, could a black hole itself be some kind of memory storage system? And if that's the case, could our entire universe be an unfolding process of information storage happening inside such a black hole? In 1997, theoretical physicist Juan Meldicena proposed the ADS/CFT correspondence, which later became widely known as the holographic principle. This theory suggests that a higher dimensional space containing gravity can be fully described by a lower dimensional theory on its boundary, one that doesn't include gravity. Just like a hologram can project a 3D image using only 2D information, our 3D universe might also be encoded on the boundary of a higher dimensional black hole. This idea was later supported by top physicists like Leonard Susskind and Gerard T. Hooft. The holographic principle not only provides a new perspective on the black hole information paradox, but also introduces a jaw-dropping possibility that the entire universe is nothing more than an information projection from inside a black hole. In 2014, a study from Harvard University took this idea even further. They found that mathematically, the initial state of the Big Bang closely resembles the bounce that happens after a black hole collapses in higher dimensional space. In other words, our universe might not have emerged from nothing. It could have originated inside another universe. After a supermassive star collapsed into a black hole and experienced a quantum fluctuation or rebound inside. This idea isn't just science fiction. Physicist Neil Turok of the Perimeter Institute in Canada once proposed the cosmic bounce model, which was later developed into loop quantum cosmology by Abhay Ushtakar's team. They aim to explain the origin of our universe using quantum gravity. Another piece of possible evidence comes from a mysterious cold spot in the cosmic microwave background. In 2004, the Wilkinson Microwave Anisotropy Probe, WMAP, discovered an unusually cold region in the southern sky. Scientists have tried to explain it in many ways: uneven cosmic inflation, voids in the galaxy distribution, and more. But none of these explanations fully satisfy the observations under standard cosmology. Some suggest this cold spot may be a kind of information residue, a birthmark left behind by the outer structure of a black hole as it gave rise to our universe. As for why gravity in our universe is so incredibly weak, this model might offer an explanation as well. Among the four fundamental forces in the Standard Model, gravity is drastically weaker than the other three: electromagnetism, the strong nuclear force, and the weak nuclear force. To put it into perspective, the repulsive force between two electrons is about 10 to the power of 36 times stronger than the gravitational force between them. According to string theory and the brane world model, gravity might leak into higher dimensional space. What we observe in our 3D universe is just a tiny fraction of the actual gravitational force. In 1998, physicists Lisa Randall and Raman Sundaram proposed the famous RS model, describing a 5-dimensional warped space where gravity can spread along the curved dimension. This gave strong theoretical backing to the idea of a black hole universe. Looking back at our universe, we find that its physical constants are incredibly precise, almost as if they were fine-tuned. From the isotropy of the cosmic microwave background, to the proportion of dark energy, to the scale of quantum fluctuations, everything seems uncannily well-balanced. Statistically speaking, a universe this finely tuned is nearly impossible to emerge by random chance. But if we are inside a black hole that inherited its structure from a parent universe, then a kind of cosmic heredity might be at work. A black hole could act like a cosmic womb, compressing the information of its parent universe at the moment of collapse, and creating a new space inside with its own set of physical laws. This idea was proposed by physicist Lee Smolin, who took it a step further by suggesting that the universe could evolve like a living organism. Universes that are better at producing black holes would be more reproductive, eventually becoming more dominant in the multiverse. If all of this holds true, then we're part of something much larger than we ever imagined. Our universe would no longer be the totality of existence, but just a piece of a higher dimensional system, an information structure, a bubble of space and time caught inside a parent universe's black hole. This might completely flip your understanding of reality, but it's also a stunning and majestic possibility. It invites us to rethink the boundary between real and illusion. Maybe the time we feel passing each day is just a trick of perspective inside a black hole. Maybe the stars and nebulae we see are merely projections of fluctuating information on a higher dimensional boundary. From where we stand, the universe is like a nested Russian doll, from the solar system to the Milky Way to the local group, and finally the observable universe. Layer after layer, it seems to keep expanding outward, which naturally leads us to ask, what lies beyond the universe? That's the beauty of science. It never stops imagining, and it tests those imaginations with the most rigorous mathematics and observations. In the coming decades, we may use gravitational wave patterns, anomalies in quantum entanglement, or the decay signatures of higher dimensional particles to slowly piece together the full puzzle of the black hole universe theory. And until then, every time we look up at the stars, every time we measure gravity, every time we wonder where the edge of the universe might be, we might actually be one step closer to the ultimate answer.